Hello again, and welcome to a video where we will look at some calorimetry practice problems. This is an optional lesson, and the worksheet for this video is posted on Google Classroom. A little motivational slide here for us. You get the fundamentals down, and the level of everything you do will rise. Truer words were never spoken by Michael Jordan. How you should use this video is look at a problem, pause the video, and then try some of the practice problems on your own. After you have an answer, you can check your work in the following slides. These practice problems are important because when you take physics next year, you'll see these types of problems again. And if you move on to AP chemistry or IB chemistry, you'll see those problems as well. They're not hard, but once you understand the strategy to solve them, they become pretty simple. So let's go ahead and try some. This is the worksheet that we're talking about. It's posted on Google Classroom if you haven't found it. The first question is a conceptual problem, and it says, when you first step on the cement, it feels hot to your feet. However, after a few minutes, the cement no longer feels hot to your feet. So explain what's happening in terms of energy transfer. So this is the scenario. The concrete's hot, your foot's cold. We know from the basic laws of thermodynamics that hot things transfer heat to cold things. That's why your foot feels warm, because it is absorbing heat. But after a few minutes, both your foot and concrete reach the same temperature. And when that's the case, heat flow stops. So your foot no longer feels hot compared to the concrete. Now, of course, this scenario wouldn't exactly work on extremely hot sand on the beach, because there, the temperature of the sand is quite hot, or very hot asphalt on a hot summer day. Let's try another type of example here. Here, we're asked to calculate the specific heat of a substance. And what did they give us? They said a 15.75 piece of iron loses 1,086.75 joules of heat, and its temperature changes from 175 degrees Celsius to 25 degrees Celsius. Calculate the specific heat of iron. Well, what we have to do is take our original equation that we learned, Q equals mCp delta T, and rearrange that to solve for heat capacity. And when we do that, we see that Q equals mCp delta T becomes Cp equals Q over m delta T. Well, let's figure out, what did they give us? They gave us Q, and that's negative 1,086.75 joules. Why is it negative? Because the piece of iron lost energy. The mass was 15.75 grams. The change in temperature is 25 minus 175, or negative 150 degrees Celsius. 25 is the final temperature. 175 is the initial temperature. Delta T is always T final minus T initial. Notice that the sign of delta T is the same as the sign of Q. That is always the case in heat capacity calculations. All we need to do now is figure out what is C sub P. Well, when we plug those values into our new equation, we get Cp is equal to negative 1,086.75 joules divided by 15.75 joules divided by negative 150 degrees Celsius, and that gives us 0.460 joules per gram per degree Celsius. That is the heat capacity of iron. Let's try another problem. How many joules of heat are needed to raise the temperature of 10 grams of aluminum from 22 degrees Celsius to 55 degrees Celsius if the specific heat of aluminum is 0.90 joules per gram per degree Celsius. Well, in this case, we don't need to rearrange our equation. It is merely Q equals mCp delta T. Everything that we were given in the problem is on the right side of the equation. Our mass was 15.75 grams. The change in temperature, 55 minus 22, or 33 degrees Celsius. The heat capacity is 0.90 joules per gram per degree Celsius. Our Q, when we plug everything into our equation, is 10 grams times 0.90 joules per gram per degree Celsius times 33 degrees Celsius. Keeping track of our units, grams and grams cancel out, degrees Celsius and degrees Celsius cancel out, and the only unit that we're left with is joules, which is good because we're trying to figure out the heat, and the unit for heat is joules. The next problem says, what's the temperature change when a 50-gram piece of glass absorbs or gains 5,275 joules of heat if its specific heat capacity is 0.5 joules per gram per degree Celsius? Okay, so what we need to do here is rearrange our equation for Q and solve it for delta T. Q is equal to mCp delta T, and that becomes delta T is equal to Q divided by mCp. Q is given in the problem as 5,275 joules, M, 50 grams, C sub P is 0.5 joules per gram per degree Celsius. When we plug this into our equation, we get a change in temperature of, keeping track of our units, of course, 211 degrees Celsius. That's how much the piece of glass warmed up. So we've solved for Q, we've solved for Cp, and we've solved for delta T. The next question is another specific heat question. Calculate the specific heat capacity of a piece of wood if 1,500 grams of wood absorbs 6.75 times 10 to the 4 joules of heat, and its temperature changes from 32 degrees Celsius to 57 degrees Celsius. 6.75 times 10 to the 4 joules is scientific notation. We can rearrange our equation for Q to solve for C sub P. So Q equals mCp delta T, and that becomes C sub P is equal to Q divided by m delta T. There I've written Q in standard notation, so 6.75 times 10 to the 4 joules equals the same thing as 67,500 joules. The mass, 1,500 grams. The change in temperature was 25 degrees Celsius. Therefore, the heat capacity must be 1.8 joules per gram per degree Celsius. The next question, if 100 grams of 37 degree water is cooled until its temperature is 4 degrees, and if the specific heat of water is 4.18 joules per gram per degree Celsius, calculate the amount of heat energy needed to cause this temperature change. Well, we have Q equals mCp delta T, and that's the form of the equation that we need to solve this problem. Our M, 100 grams, delta T, negative 33 degrees Celsius. Our heat capacity, 4.184 joules per gram per degree Celsius. Sometimes you'll see the heat capacity given as 4.184, sometimes as 4.18. Either way, it will be fine in our calculations. So we want to know, well, what is Q? Q is equal to 100 times 4.184 times negative 33, or, keeping track of our units, of course, a negative 13,807 joules. In other words, that amount of energy was lost by the water. Well, there you go. I hope you enjoyed our solution key video, and I look forward to our next opportunity. Take care.